In this module, we will investigate a graph algorithm that has tremendous value, not just in computer science, but in a number of disciplines. It was first invented in the 1950s by Edward Dijkstra, and it's fundamental to understanding how we search through graphs, where they're not just structural, but there are weights and values associated with the edges. Consider the following graph. There's some vertices and edges between them, but there are two differences. First, these edges have an orientation. There's an edge from vertex V0 to V1, but not in reverse order. This could represent any number of potential relationships between the vertices. For example, there could be one-way streets. There could be shipping lanes. Any number of situations where you have a flow of information or data or goods from one location to another. In addition, each of the edges has a weight associated with it. Those weights could reflect a real-world concept, like mileage or cost, but there could also be other abstract concerns as well. If I look at this graph, some questions naturally arise. For example, what is the shortest distance from vertex V1 to V3 when you also consider not just the number of edges it traverses, but the total sum of the edge weights that you encounter? Starting from vertex V1, I traverse the edge to vertex V2, and I incur a cost of 3. And then I go from vertex V2 to vertex V3, I have an additional cost of 5, so I add that together, I get 8. And that naturally leads to the next question, well, what's the shortest distance between any two vertices? Now you might start with this and imagine that I just have a graph that I'm trying to traverse. And if you're asking the question, what's the shortest distance between any two vertices, you might think, well, I have to traverse n times once, starting from every single vertex, just so I can figure out what the shortest possible path is between any two vertices. What's really interesting is I don't need to undertake such an exercise. There has to be some way to avoid generating all these possible paths. And that's what the real elegance of this algorithm will be. But let's make some following observations. First, the edge direction matters. If I take that one edge from vertex V4 to V3 and I flip it around, so now there's no way that vertex V4 can ever go anywhere. It's now been disconnected in a way from the graph. So I have to be very careful to understand not just the fact that the graph is connected, that there's an edge between these vertices, but I also have to pay attention to the orientation as I'm traversing the graph. Second, well, if I look at vertex V4 again in my original graph, and I see that there's only one edge emanating from it, and that's the edge that takes you to vertex V3. That's some structural information which is local, but it has global implications as well. For example, if I find the shortest path from vertex V3 to every other graph node, I now have actually computed the shortest distance from graph node V4 to those same ones, because all I have to do is add 3 to those computed distances. Because of the structural properties of the graph, I know that V4 will therefore have its computed distance based entirely on what V3 had computed. This suggests that there's an interesting opportunity to reuse some of the problems. As I'm solving the graph, I don't need to do it all from scratch. There may be opportunities for reuse. We'll see that come up in the algorithm itself. One more observation. In this graph, you would normally say, well, the shortest distance must be the direct edge. But since every edge can have its own weights, it turns out that's not the case. If you see from vertex V2 to V3, the single edge that traverses has a cost of 5. But if I go from V2 to V4, and then from V4 down to V3, I've accumulated a total cost of 4. And if I'm interested in the shortest distance or the least amount of cost to go from one point to another, that would be the path I would choose. So sometimes you look at the graph, which has this embedded a lot of rich semantic information. And the kind of questions that I'm looking for are not just, is it possible to go from point A to point B, but what's the accumulated cost of doing so? And then I want to find the minimum cost, because that's, after all, the most interesting problem. So how do we go about solving this? Turns out there's a technique called dynamic programming that was invented, as I mentioned, in the 1950s, that provided a framework for solving these kind of problems. On its own right, dynamic programming is an extremely important tool in your tool belt. And when I summarize this module, I'll introduce some other domains for which it's also extremely useful. The way that dynamic programming works is to take advantage of the fact that you can solve subproblems that are of interest to other parts of your solution. And the way that it approaches this task is by starting with the simplest, the smallest, the most constrained form of the problem. And then slowly, ever so slowly, it starts relaxing those constraints, dynamically adjusting its best estimate of the cost to reflect a new reality as you uncover different opportunities. With this in mind, let's apply the all pairs shortest path to a specific graph and see if, as we try to solve that problem manually, we won't uncover some ideas of how to implement an algorithm. If I have this graph with these 5 vertices, I want to compute, when I'm done, an array, which is a 2-dimensional array, indexed on both u and v, that represents the estimate of the shortest path going from u to v. This matrix may not be symmetric because my graph is, after all, directed. I may be able to go from u to v. I might not be able to go back from v to u. If I look at this graph and I just put down the edges, and I have the diagonal all 0 because, after all, there are no edges from a vertex to itself. But all the others where there is an edge, I put down the edge weight that exists. So, for example, I can go from vertex 0 to vertex 1 and incur a cost of 2. And that's what you see in the top row, that first non-zero value there. When there is no edge between 2 vertices, I have nothing to say about the lowest cost between those 2 vertices, so I put infinity as my estimate for what I believe the cost to be. So if I start with my initial cut, this is what you would call the most constrained form of the problem. How do I estimate the best or the lowest cost to go from any vertex u to any other vertex v? I start with the edges that I'm given, and that'll be my first and quite reasonable estimate for that total cost. If I start with that, how do I proceed? The way that dynamic programming works, as mentioned, is you relax the problem a little bit. Let's relax it as follows. Not only am I going to allow direct edges, I'm now going to allow any path that also includes vertex v0. And if I make that small adjustment to my domain, let's look at what it gives me. There are 2 updates marked in black in the matrix. Let's look in particular at the first one, the shortest distance from node 3 to node 1. In this particular arrangement, there is no direct edge between 3 and 1. So my earlier matrix had infinity there. But now that I'm allowed to go through vertex v0, I've uncovered a lower solution. 8 plus 2 is 10. And I just marked it in there. And that one observation, recording the fact that I can now go from 3 to 1 with cost of 10, might be useful to some other particular shortest vertex calculation. And so I'm using this distance matrix as a platform to storing my best estimate that I know to date. And every time I uncover a better estimate, I plug it right on in and keep on going. And so I'm refining, constantly refining my solution until I get to what we can prove is the shortest one. Although I leave the proofs to academic textbooks, here I'll be showing you the code and demonstrating their application. The other change in the matrix is from 3 to 4, and it has the same reasoning. I can go from 3 to 4 through vertex 0. And what you want to do is consider, now that I've made that small adjustment, let me adjust one more time. What if now I allow you to not only use direct edges and not only use edges that happen to go through vertex v0, now you can use edges that go through vertex v1 as well. Here, similarly, I've got 2 more adjustments to make. I can now go from vertex 0 to vertex 2, for example. And so you continue this process repeatedly until all the vertices are allowed in any path. And so what you did is you took a problem that seemed insurmountable, or at least seemed like it was going to be a lot of work, and broke it up into very distinct iterative solutions where you start with the most constrained form of the problem, just the direct edges, and then you slowly but surely allow the problem to change. Just allow paths that include vertex v0. Just allow paths that include vertex v0 and vertex v1. And you keep on going until all the vertices are fair game. And in doing so, you will record the solution. Now, in addition to storing this distance matrix, which records the total cost that you've incurred so far, we'll also have another matrix, which is the predecessor, or pred array. So to use the pred, I can now reflect on what it gives me. If I have the best cost, I also want to record, well, what was the path that got me there? And you might think you have to store long lists to record all that information. But fortunately, we can encode the same information in a tabular form, just like we've done with the total distance. For example, the top entry in this matrix, the fact that now I can go from 0 to 2, and that total cost is 5, in the code, it will remember that that cost remembers that to get to 2, you had to go through vertex 1. And then vertex 1, remember, to get that cost, it had to go through from vertex 0. And so I can recover the path between any two vertices by starting at the terminal one and work my way backwards through the predecessor links. The distance table then records fundamental information about the graph, and those hard-earned results can be used to solve all the other questions that remain in the graph regarding the shortest distance from any vertex to any other vertex. To implement the all-pairs shortest path algorithm, we'll use dynamic programming approach as first identified by Floyd Warshall. As I've already discussed, it creates two matrices to store information about the progress of the algorithm. First one is dist, that keeps track of the best estimate for the shortest path between any two vertices u and v. The next one is the pred, which remembers the predecessor link when you need to recover the solution once you're done. This initial stage of the algorithm is done using the information that's available. As we said, dynamic programming starts by working on small problems that are the most constrained and then slowly relaxing those constraints. Clearly, the most constrained is when you only allow direct edges. So this initial stage of the algorithm will do a nested loop to go for every pair of vertex that exists. It will assign the diagonal entries of the dist matrix to be 0 because there are no edges between a vertex and itself. If there is an edge between u and v, then it will assign the weight of that edge as being the best estimate for the shortest distance between u and v. And it will remember that by putting in the pred matrix, that the predecessor from u to v is to follow from vertex u. If it turns out that there is no edge, then without any other information, it assigns infinity to the entry in the dist matrix, and it assigns -1 to be the predecessor, which is reflective of no predecessor known at this time. Once that initial stage is set, the dynamic programming algorithm is ready to take off. If I look at the algorithmic analysis so far, you see a nested for loop, so I know that at least it's order n squared to compute that initial stage. If you notice, the spec sheet says that this behavior is order n cubed, and the reason why it is because of the nature of the dynamic programming algorithm. It starts with the most constrained problem, namely the only costs you can assume are the direct costs by following an edge from u to v. It starts to slowly relax those constraints, allowing paths that use vertex 0, and then vertex 1, and then vertex 2, and so on. And this outer loop here, for each t in the vertex set, now sets up a triply nested loop. So, using the same logic, that's how I can determine that the overall performance of this algorithm is n cubed. The key step in the dynamic programming exercise is to understand when you've encountered a new piece of data that gives you a better estimate for the distance between u and v. The way that it works is by slowly relaxing your constraints and allowing extra vertices to be included in the path. And it comes down to this one simple statement. And the beauty of dynamic programming is if you can represent your problem using a matrix that has an estimated cost, and you can set it up so that you're looking for the minimum cost, all you're trying to do is optimize this function. this is a common concern in industrial engineering and operations research, which is where these algorithms came from. Let's look at the key step. If you ever find, as we did in some of the earlier examples, if you ever find that a direct edge from U to V is actually longer than going from U to some other intermediate vertex and then V again, you've actually got a better cost than what you had before. And that is exactly what this formula says. Is the distance from U to some intermediate vertex T plus the distance from that intermediate vertex T to V, is the sum total of that less than what you think is the best cost from U to V? If it ever is the case, you've uncovered something and you need to record it. And when you look at this statement, we start with the first premise, which is I can understand that best when I think about the initial stage. I first start with only the direct edges, and then I consider what if I add another vertex to the mix. But you should also remember that dist U comma V really is storing the best estimate at any stage in the algorithm for the cost you would incur from traversing from U to V. And so at any stage in the algorithm, if you ever uncover this intermediate vertex T that actually shaves off some cost points, you can take advantage of it. And the way you do so is by recording that new cost in your distribution matrix, and then remembering the predecessor link. So you can remember this later. Should it be part of the final solution, you know how to recover that. And so instead of the existing estimate from U to V, you now have a better cost estimate, which goes from U to T back to V. And for that reason, I changed my predecessor link from U to V to make sure that I pick up the cost that it went through T as well. With that in mind, we're now ready to talk about the code. Before we start in the implementation of the all pairs shortest path, I'm taking just a little bit of a tangent to present a different implementation as a better way to explain exactly how and why dynamic programming works. You may be familiar with the Fibonacci series, the idea that you start with two numbers, traditionally 1 and 1, and you add them together to get 2, and then you subsequently continue that process, going from 1, 1, 2, 3, 5, 8, and so on. It's an old series of integers, and when you think about how you code that up mathematically, or at least how I would code them up in Python, I may turn it into the following code. I start with this idea that I'm looking for the nth Fibonacci number. And I'm going to state in my documentation, I'm going to use poor recursion. If it turns out that I'm looking for the 0th or the first one, using mathematically the idea that the first two numbers in the Fibonacci series are the 0th one and the first one, I want to return 1, because after all, I start with 1 and 1. However, if I have a higher number, then I can simply say, you know, you just want to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. As a recursive definition, it's quite clear. As implementation, it's quite poor. But let's see it so we can understand why that's the case. If I look for the 0th or the first Fibonacci number, I'm not surprised, they're 1 and 1. If I go further to say, give me the 5th Fibonacci number, that's 8. 1, 1, 2, 3, 5, and then 8. All looks good. If I keep this on going, you'll start to notice something a little unusual, I imagine. I'm now doing the 20th one. Depending on the speed of your computer, at some point, it starts slowing down, and it doesn't make any sense. Why is it now, when I'm looking for the 31st one, it's taking longer and longer? Surely this is just a mathematical computation. The problem is in how the recursion is set up. And so this is exactly the wrong way to implement the Fibonacci implementation. And the reason is because look at how the problem is set up. Normally, we want to tackle problems by breaking them up into smaller problems that we can work on. And it looks like you're doing that because to solve a Fibonacci, find the nth Fibonacci number, I just need the n minus 1th and the n minus 2nd one. So it looks like I've broken the problem up into two smaller problems. Unfortunately, each one of those has to themselves be broken up into two more smaller problems as well. And these smaller problems are not half the size of the original, they're only one smaller. And so if I did this in this way, this is the exact wrong way to implement Fibonacci. The reason why I'm mentioning this concept here is because what are the subproblems that Fibonacci is working with? It's trying to solve the subproblem n-1 and another subproblem n-2, but it's not doing anything to actually store that information. Dynamic programming gives you the ability to work on problems, and every time you find a solution that looks better than the one before, you store it. And then you can remember that for the next time you go through. So by an interesting analogy, if I just make a small little change here, which says I'm going to keep track of past Fibonacci numbers. And so if I get to 0, 1 here, I'm just going to answer the following question. Am I asked to solve a problem for which I have seen in the past? If I have, I just return whatever it was that I saw in the past. Now, it may be the case that I've not seen it, so I go forward. So here I would just record for posterity that the past Fibonacci number of n is equal to 1. And this is the case that's more interesting. I want to return the sum of Fibonacci 1, I'll call it total, plus n-1. But I don't need to compute them. If I store those results for posterity, they'll be there the next time I need to have the 10th Fibonacci number or the 20th one. So I only need to compute each of these subproblems once if I take the time to store that information for future use. So in this recording setup over here, I will record that the past Fibonacci number, this case is n, is equal to total. This might, if I look at this, I might be able to come up with a more efficient way of implementing Fibonacci. Let's see if I've done that. Now I'm still getting the right Fibonacci numbers, but look what I'm actually keeping track of. I actually have all the past runs of the n-1 values. They're all being stored there for me to use. So let me look for the 30th one. It was noticeably faster. Let me look for the 40th one. And there's no stopping me now. I'm just keeping track of all these past results. And the storage of past results are what makes this particular implementation of Fibonacci so efficient. And it's a direct analogy for how dynamic programming uses a two-dimensional form to store a matrix of these past results that allows it to be as efficient. So let's get started. I'm going to start with a graph, and since this module is intended to be standalone, I'm using a very simple structure of recording that graph. In this case, the graph is itself going to be a dictionary where I have a set of vertices, and for each one, I'm going to record the edge and the weight that's associated with the edge. So here, I've got a vertex 0 in the graph. He has two neighbors, 1 and 4. The edge from 0 to 1 has a cost of 2. The edge from 0 to 4 has a cost of 4. So this is a quick way to represent that graph that I had just described in the PowerPoint slides. What I want to do now is write an all pairs shortest path algorithm that takes advantage of this particular structure. So that's what we're going to do. To do this, I need to write my all pairs shortest path. And it takes a graph. And what is it going to return? Well, we'll start with this idea that it's going to return the distance structure as computed. Now, I'm building up this code incrementally, so I know we have a predecessor structure we have to keep track of, but let's first do the core part, and we'll explain how that all fits in. I'm going to start with an empty dictionary, and I know that this is going to be a two-dimensional array, and so what I'm going to do is set the problem up. I know my graphs, make a little note of this myself. The key are the vertices. Each edge has a weight, and that's encoded as well. So I want to do the following. For every vertex in the graph, I need to record distance to those as well. So my dist variable here in Python will be a two-dimensional array. For every vertex v, so now I'm doing an n-squared nested loop where I'm going to go for u and v would be all the vertices. I will set this up as follows. Set distance uv to be equal to the maximum int. At some point, I need to have some value to represent infinity. I could choose an arbitrary value. Python has a nice ability in its modules to have a max int defined in the sys module. I'll use that for my representation of infinity. When I'm done with this, I will say I know for a fact that dist from u to u is equal to 0 because I know there were no edges from a vertex to itself. And I have to now look at my edge weights and say, well, for the edges that actually exist, what can I do with those? Now, the edges that actually exist, I'll find those by looking at my neighbors. I've got a graph G. The neighbors of a particular vertex u are, in fact, found in this G of u. And so for that, each of those vertices, I will say that the distance, the best estimated distance of the shortest path from u to v is nothing more than the current edge weight that I have associated with uv. When you look at this the first time, it does start to look a lot like Python speak, but that's after all the nature of representing matrices in Python. It can get a little syntactic. But this corresponds to stage 1 of the algorithm, which is set up the distance matrix. Let's see if we've at least done that. So I'm going to run this. We're going to compute all pairs shortest path on the graph that I have. And if you casually look this over, you'll see that every now and then you have infinity represented by that very large number, 2 to the 32 minus 1. Every now and then you have a 0. Right here, this is on the diagonal. Just like in 1, it appears there as well as down on the other side. And at other times, you actually have an edge weight that records the actual weight associated with an edge from vertex 0 to 1, let's say. So at least I've got my distance set up properly. Once I have that, I have to move on to the next stage of the algorithm. And in that stage, I need to do my triply nested loop to allow the algorithm to actually exercise its dynamic programming skills, starting from the most constrained problem, which you see here, and slowly adding on different vertices to be used. So we'll do that as follows. I'm going to go for some midpoint, some intervening vertex mid. And I'm going to go for every vertex u in G, and then for every vertex v in G. This is the classical triply nested structure that we've seen. For each of these three, the midpoint, the new vertex that I'm trying to add to the mix, as well as the original u and v that I'm trying to determine the shortest distance between, I need to compute the new len. And the new len is going to be, well, give me the best cost that I have from the distance from u to that intermediate vertex mid, plus the existing best cost from the distance mid to the terminal vertex v. And if it ever turns out that new len is less than the best cost that I have, and I use strictly less than because I don't want to waste my time doing less than or equal to. There's no point in computing a different shortest path so they all have the same weight. Under this circumstance, I can now say with authority that the distance from u to v is actually that new len. This will compute the actual results of the all pairs shortest path. And if you look at the code, it's a common feature of dynamic programming. You look at the code and you just don't believe it. It looks too simple. Reflect on the nature of dynamic programming, however. All the logic is encoded in the arrays that you're storing. The code is simply relaxing the constraints, one new vertex at a time. And it's the matrices that store the information that record all the different possible runs that have been done, much like I showed with the Fibonacci. The only thing I need to now do is not just compute the shortest distance, but to do the predecessor link so I can actually recover the solution. Let's just verify that this works first, though. The first thing you'll notice is that all the infinities have gone away. That's a sign of a graph that is not just connected, but you can actually get from every vertex to every other vertex. The other thing I would point to is that without having a graphical representation, or even to show you what the solutions are, there's no point in wondering if these results are correct. And that's why we have to do the predecessor link so we can actually generate some of our solutions. Recall from the algorithm that not only do I want to keep track of the distance, I want to keep track of the predecessor links for each vertex u and v. When I set up my initial solution, I know that the predecessor on the diagonals are, I'll use none. There is none, because you can't have an edge from itself to itself. However, what do I do with the others as well? Well, anytime that I assume that the distance between u and v is infinity, it's exactly at that time that I would say I have no information about the predecessor link. So that makes sense to me. Finally here, when I know that I've got an actual edge, I need to record the fact that the predecessor from u to v is u. That small little change is all I need to do to update the predecessor set. What do I need to do down here? Well, the only change is to reflect the fact that now that I've computed this new best estimate for the shortest distance from u to v, I have to record the fact that at v, the distance from u to v, I'm no longer going back to u, I'm going back to whatever it was that the midpoint went back to. So I go from not just u to v, I go from u to mid to v. So if you're going to work your way backwards, I start at v and I go back to mid. That helps explain why that is set up the way it is. So now I'm not just returning the distance, I'm going to return the distance and then some predecessor matrix. When I run this, the code looks more or less the same. The output does. What I have is I've got two different arrays here, and let me pull those out so we can see them in better form. I've got my distance, which we've already seen. That demonstrates there are no more infinities there, and I can make it from every vertex to every other vertex, and I've recorded what I believe are the lowest costs. Predecessor has a number of potential interesting things here. It has a lot of nones, but don't forget, you need to have the nones every time you have a diagonal entry in the matrix. So there should be 5 of them for every one of the entries. I have this information, but what do I do with it? I need to be able to create a function that somehow extracts the solution from the predecessor links. And the way it does this is, again, by walking backwards. Starting at the vertex v, the terminal one, I can always work my way backwards to find its earliest, or not the earliest, the one prior to it. And then before you know it, you've walked away all the way back. Let's show how this works. I need to find a method called construct shortest path. What is it going to take as this input? Well, I want to find the shortest path from S to T, and I start with my predecessor matrix that's been given to me. This idea is to reconstruct shortest path from S to T using information in pred. I know that it's going to be some kind of path that I'm going to store as a Python list, and as I build it up, I will return it. To actually do this, well, I know that if I actually have a path from S to T, the T must be in the path. So I'll put that there as my starting point. And then what I'm going to do is work my way backwards. And I'll say, well, as long as I'm not at S, which after all, I'm looking for the shortest path from S to T. So as long as I'm not at S, let me find out how to go. You reverse the predecessor links to go back to the matrix entry whose vertex gave you that distance. And again, a lot of this does look like magic because it's so short, the amount of code, but it's fundamentally based on the principle of dynamic programming, which is use the matrices to store not just the computed best cost, but information that gives you the ability to retrieve the entire path by just doing it one predecessor at a time. So I decide to go from my predecessor, S to T. So I want to start at T. I want to work my way all the way back to S. Well, let me go backwards. If it turns out that T is none, then for whatever reason, this is my escape hatch. This should never happen. But it's good to have at least some protection against potential defect. I now have made one step towards my goal of getting back to S. And I want to return a path that indicates the direction, starting from S all the way ending up at T, which means that I have to take this value and insert it at the front of the path. And then it's going to continue, work its way back, until eventually it reaches the source. This kind of logic is based on a properly constructed PRED table, which the dynamic programming does. So now we have all the parts in place to be able to demonstrate how this would look. I start with my two graph tables that I produce. This is my distance that tells me, for example, the distance from 1 to 4, distance of 1 to 4 is 4. So there must be a shortest path between 1 to 4 that only accounts for a total of 4 on the edge weight. Let me look at the solution that is actually produced. Let's construct the shortest path from 1 to 4 using my PRED table. So it turns out you go from vertex 1 to vertex 2 to vertex 4, and that gives you the shortest distance from 1 to 4. If you look at these PRED tables, and again look at the brevity of the code, really try to understand how dynamic programming works. It's storing a tremendous amount of information in these two-dimensional tables. It's recording past results that were useful then and are useful for each subsequent iteration through the dynamic programming. You will always converge on a solution because it doesn't matter which way you go. Paths are consecutive, and you string them together by logically accumulating your edge weights as you traverse on the graph. So I don't even have to worry about the order by which I'm traversing the graph. I blindly let the dynamic programming algorithm do its work, and it will uncover in direct proportion to this relaxation technique each subsequent vertex that could make a potential path smaller than it was before. Its brevity is noticeable. Its performance is exceptional. This is the reason why you can have trucking companies ship the goods all around the country, because they can generate tables of shipping charts that may have 200 warehouses or 1,500 stores. If I have 1,500 locations to get to, that's only n cubed. If that had been n raised to an exponential power, like 2 to the n, it would be impossible to solve this. And anytime you find yourself with a polynomial algorithm, either linear, order n, or quadratic, order n squared, or even n cubed for that matter, it's actually still in the space of what we would consider to be efficient algorithms that will generate a result. And think of the alternative. You might have thought at the beginning, well, the only way to determine the all-pair shortest path is to construct every single path that exists between every single pair of vertices. That is an exponential search space. That would be a very hard task. We're not solving that task. We're getting the right answer because we're using dynamic programming to achieve it. Through successive relaxations, it's able to achieve that in polynomial time and produce impressive results. The all-pair shortest path algorithm is a classic demonstration of the power of dynamic programming. Once you've understood that technique, you can find 20 or 30 other instances. For example, in bioinformatics, a lot of times they're very concerned not just about sequencing genomes, but trying to find two genetic sequences and how close they are in terms of the mutations. That's called the edit distance problem. And using dynamic programming, you can compute the minimum number of mutations required to convert from one gene to the other. And it doesn't matter that the genes are 1,500 or 2,000 bases in length. Minimum path of the dynamic programming will achieve it in polynomial time. And so you have an efficient algorithm. So even though we have problems that seem almost intractable to a human, 1,000 or 2,000 elements in the size, for example, because it's polynomial, it's able to be done in an efficient manner. And so this notion about algorithmic families that we spend time talking about in the sidebar is really important because it differentiates the kind of algorithms that you can use. any algorithm that's log of n behavior or order n, or in fact order n to any constant power like n squared or n cubed, is deemed officially efficient because it doesn't blow up to deal with problems that are too large to fit into the computer. Other approaches, such as the brute force approach, or one that has no choice but to search every possible path, those fall into the exponential side, and you can only solve small problems, and the attempt to solve larger ones is doomed to fail because the search space is simply too large. What dynamic programming brings to the table is another skill that you can apply if you can identify the subproblems and how to convert two subproblems whose composition can yield a better result than the best estimate to date with the earlier iterations through the dynamic programming loop. This concludes the all pairs shortest path module.